Morning, everyone. My name is Ken. I'm very happy to have this opportunity to share our project here. And the title of my presentation is Explore the Relationship between Wastewater Viral Signals and COVID-19 Hospitalizations in Ottawa, Ontario. So firstly, what is the wastewater viral signal? The SARS-CoV-2, the virus which causes the COVID-19, can be actually detected and quantified using the wastewater surveillance data and by some techniques. And that produced the wastewater viral signals. So from the plot, you can see that the wastewater viral signal is able to predict the trend of the COVID-19 hospitalizations. And however, this association is not simply linear and also not consistent over time. So in our project, our goal is to study this nonlinear association between them. Firstly, we did a correlation analysis. So in general words, we use the rolling correlation. And for each rolling window, we allow the time lag between the wastewater viral signals and the hospitalizations to vary. So really what we want to see here is the how the correlation between them varies over time, and also how the time lag between them varies over time. So in this plot, I'm showing the results of this analysis. The first plot is the correlation over time, and the second plot is the time lag over time. So I highlighted the delta wave because during the delta wave, the correlation between them is not very high in Ottawa. And we also did a distributed nonlinear lag model. So I won't go too much detail about the model. I'll just summarize what we included in the model. So we have the time varying intercept, and then we have the nonlinear association from wastewater viral signals. And we also included the simulated vaccination effectiveness. So on the left side, the plots I'm showing the simulated vaccination effectiveness against hospitalization under 3 different scenarios. So for the first scenario, we assume there's no waning of the vaccination effectiveness. So it's basically just cumulative vaccination doses. And for the second scenario, we assume mild waning. And for the last scenario, we assume the further waning during the Omicron period. So on the right side is the estimated hospitalization versus the true hospitalization. You can see the model fitted pretty well. And the second plot should be Omicron period. That's a typo, sorry about that. And lastly, I just spent 1 page to summarize our findings. So first, we found that the z-axis is the relative risk of the hospitalization. So we found that when the wastewater viral signal increases, it can be used as a marker of the increases in the hospitalization. And also we can see that the first plot, that's the pre-Omicron period, is pretty different from the Omicron period. The lag association is like the relative risk of hospitalization go down first and then go up for pre-Omicron period. But for the Omicron period, it's go up first and then go down. And the highest relative risk happens around 8 or 9 time lags. And that's everything about my summarize. And thanks. I look forward for the questions if there's any.
Someone wants to discuss?
Yeah, sure. Yeah, I have my poster ready outside, so.
Yeah. So we'll go to the next talk.
Hi everyone, I'm Bushra Majeed. So I'm going to talk about the co-circulation of influenza and COVID-19 in the presence of vaccination. The main objective of this project is to see the impact of influenza on COVID co-circulation because of the very similar symptoms of both of these diseases, and it can impact on the COVID-19 testing speed. And the second one is to explore the optimal and minimal vaccination coverage required for both of the two diseases, influenza and COVID-19, to avert the twin peak of both of these diseases in the same season. So this is our deterministic model in which we have started from the 4 susceptible classes, vaccinated with COVID, vaccinated with COVID and flu, and vaccinated with flu, and those which are unvaccinated. So these are the 4 susceptible classes because the vaccines of both diseases are imperfect. And further, we added the isolation compartment. The individuals, because of similar symptoms, they can isolate them before they are diagnosed for the COVID test. And after diagnosis, they can move to the isolation for the, if they are positive to the COVID, and if they are negative, they can just release, we can just release them. And for the testing, instead of taking the constant rate for the diagnostic, we have modified that function with the Holing type 2 function. And also we are considering the effectiveness of 4 doses of the COVID-19 vaccine. So here are some results of our simulations. The first one is that with the testing capacity, if we increase the testing capacity for the COVID test, we can see a clear delay in the COVID-19 infection. But there is an increase in the influenza infections because early detection in the COVID-19, we will release the infection with the those who are infected with the influenza. They can make more infections if they are diagnosed and released earlier. And the second one is for the varying of the transmission rate of the influenza. We considered that case because of previous last 2 years there were a few cases of the influenza, but in the coming season we can expect more susceptible for the influenza. And the bottom 2 plots are for the vaccine coverage of the both flu and impact of the increase of the vaccine coverage of booster dose of COVID-19 and influenza vaccine. And we can see that in influenza vaccine coverage, if we increase that, it clearly delays the peak of both influenza and COVID-19. And further, we incorporate the influenza and vaccine, COVID vaccine with the mask wearing, 20%, and we can see with the mask wearing, if coupled with the vaccine, it can clearly mitigate the COVID-19, but it can also control the outbreak from the influenza. Further, our sensitivity analysis is in the progress, and that's it. These are the key findings. In net conclusion, we can see that the increase in moderate vaccine coverage of both diseases with around 20% with the mask wearing can mitigate the COVID-19, and it can also prevent the influenza outbreaks. Thank you.
All right. Good morning, everyone. Really happy to be here. I'm Ariel Mundo. I'm with the University of Montreal, and I'll be talking about reproducibility using generalized additive models to analyze longitudinal data. So biomedical research, this is same to biomedical research. In biomedical research, people collect data over time, longitudinal data, repeated measures, because most of the time we're interested in seeing how things change over time. So you can have, for example, a treatment group or a control group, and you want to see what the effect of the intervention is over time. So this is done over and over and over. Now, biomedical researchers typically use 2 types of analysis to analyze longitudinal data. One being the repeated measures ANOVA, or the other one being linear mixed models, which I have a small equation here at the bottom. This is just the repeated measures ANOVA case. In a linear mixed model, of course, we will have a random effect here. But basically, the point of this is that people use this because it's what we have always used before. And there's a limitation. And I'm sure from the data we saw before with the COVID presentation and data the other peers have presented before, we have seen that over time, the signal we collect is rarely linear. So what this causes a problem, because when we are assuming a linear mixed model or repeat the measures ANOVA, we're assuming the trend is going to be linear over time. So this is a limitation that continues to happen in biomedical research, and the idea of this work is to show people ways to overcome this. So I won't go into all the details, but basically the goal of our work is show biomedical researchers that they can use generalized additive models, which are a class of models that allow the data to speak by themselves, because you're not assuming a linear relationship. So basically we can have some splines, and then we penalize the splines, and when we add them together, we can recreate any trend over time, not just linear trends. So here, for example, we have some simulated data, and we simulate trends. So this is data from a study where they were having 2 types of treatment of, I think it was tumors. And then we see that there's a trend, there's difference in the trend, but if we do a linear mixed model, repeated measure number, we're gonna have a line here, which creates biased estimates. If we fit a generalized additive model using the splines, we get much better inference, and we're able to actually have a better estimate on what's going on. And this can be potentially important in the case of clinical trials or longitudinal studies. So the goal is to make researchers familiar with generalized additive models, show how they can use them and how they can get better inference from the data. And this is work that has started at the University of Arkansas where I did my PhD and has continued at the University of Montreal in the Natural Lab. So I'll be happy to take any question later at the poster session.
Okay, good morning to everyone. I'm Norma Forero. I'm a PhD candidate at the University of Montreal. And today I want to share with you using universal ordinary differential equations for disease ecology modeling. This is part of my PhD thesis. It's going to be super simple, but I want to invite you to feel excited as I feel with my PhD thesis. So, since this is the applications of this topic to disease ecologies, well, this is a system that I guess that most of you are familiarized with, and SIR models or SIR models, and it's how this can be applied to different kinds of infectious cycles between humans or between animals, or this can be as complex, as simple as we want. But for all the people that have worked with this, the hardest part of this model, well, the first part is hard because we have to build the model. And the second part is let's play with the parameters. And when we talk about the parameters, it's when we say, oh no, I don't want to get into that. Just not. But there are certain methods that help us to estimate these parameters. And it has certain advantages and disadvantages to work with it. But a method that now I'm working with during my PhD is with scientific machine learning, which what can help us is to, instead of having this parameter just like a number in it, we can replace it with a neural network, which means that we can still have our model based on differential equations, but we can do the estimation of the parameters now with neural networks. And this neural network is going to be trained with our own data. But since I work mostly with disease ecology, as we know, it started getting challenging at the time of working with small amounts of data. So something that I'm still working with is what it means to have a small amount of data, 3 points, 100 points. So I'm still working on it. I'm still trying to discover how much can my model learn according to the data that I have, and how to have a better estimation of the parameters using this, based on scientific machine learning. So basically, that's what I want to share with you. Thank you so much for hearing my presentation, and I hope it can be exciting as I feel with my thesis. So thank you.
Hi, good morning, everyone. My name is Xiaoyan Li. I'm from the University of Saskatchewan. So today, my topic I would like to present is an algebraic framework for stock flow diagrams and dynamical systems. So we know that the stock flow diagram is a very important building blocks to build dynamical models. So in this work, what we have do is we just create a new framework. With this new framework, we can create a quite complex stock flow diagrams from the small pieces. So, in the beginning, let's see what is the category of the stock flow diagram. So for the left graph, it shows the category that we have built for the stock flow diagram. We can think of the category of the stock flow diagram as like a blueprint to represent the structure of the stock flow diagram. And for a stock flow diagram, we can think that is like an instance of the category. So in the right, we have shown an example of the SEIR stock flow diagram, which have been created by the our software. So we have used the categorical database structure to represent the stock flow diagram, which have built based on the category that we have built on the left side. Okay, so this method have a very, one of the advantage of this method is this strictly mathematically separate between the stock flow diagram syntax and its semantics. So for example, we can have a stock flow diagram. So the stock flow diagram, we can think it as a syntax. Then if we take in a stock flow diagram, then we can map this stock flow diagram to different syntax. Semantics. So the first semantics can be the ODEs and the solutions. And then we can also map the stock flow diagram to the causal loop diagram and the system structure diagram. In our future work, we would also to explore more semantics of the stock flow diagrams like the statistical differential equations. Okay, so now let's see our most interesting work is what is the compositional framework of the stock flow diagram. So in our compositional framework, what we have do is we can build a quite complex and big stock flow diagram by gluing from different and multiple small pieces based on their common parts. For the theory we have used is to take the push out of the structural cospan and decorated cospan that we have been employed to used to represent the open stock flow diagram. So we have an example here. So if we see the example, that is we have an SEIR model and also an SEIV model, we can take this to the left figure, this two model as small pieces. Then we can glue this two small model based on their common interface. We can see that is like the SEI and SE and the I compartments. After gluing this two small model, then we can build the relatively complex model of the SEIRV model directly. Okay, the second framework is the stratification framework. To use the stratification framework, we can build a stratified model based on the small pieces of stock flow diagrams. So the theory we have been used is the stratified stock flow diagram is the pullback of two stock flow diagram. So for example, is in the right figure, we can see, for example, if we have an SEIR model here, and then we can create a small model like the age strata model. Then we can take the pullback of the SEIR model and the age strata model. Then we can create the stratified SEIR model by the age group. So I think my final comments of our work is this framework will be more powerful if we build more complex models. Okay, thank you so much.
Good morning, my name is Adriana and I'm from University of Manitoba. And I'm going to talk about travel suspension in Canada, US, and Europe during COVID-19. As we know, the 2019 global pandemic has become one of the most severe pandemics in recent history. While air mobility allows more passengers to fly to more and remote destination, it also plays an important role in helping local epidemics turn into global pandemics. We observed this phenomenon for influenza, MERS, SARS, and Ebola. So we found a data set which is open source. We have a screenshot of it. It does have a lot of limitations. Unfortunately, the way the origin and destination are computed will have, as you can see, a lot of them not available, which is not very good. And there's no cross-validation or cross-checking with external data source for this data set. But we still used it. We did some data cleaning. We removed all rows that didn't have either an origin, destination, or both. And we also removed loops on them. So that means flights that start and end at the same airport. After we did this, we did some data processing. We only took a subset that contains Canada, US, and Europe. And then we also included other information in the data set. As methods that we used social network analysis and graph theory methods. In this slide, we can see volumes for Toronto Pearson Airport. Let's see here, and Chicago O'Hare Airport. In both, we can see that the lowest number of passengers for both airports happened in 2020 May. Furthermore, we looked at community detection algorithms. We looked at several of them. On the slides, we have laden community algorithm and wrong community algorithm to see how the number of community is and the maximum size of the community changes over time. Lastly, we looked at centrality measures. Between a centrality highlights the potential of airport to act as a channel in the spread of infectious disease, which means airports with high between centrality may be used in disturbing the international spread of infectious disease. We also looked at closeness centrality, which represents the average length of shortest path between a given airport and all other airports through the network. And we can look at, so this can measure the accessibility of an airport from other airports. As further work, we like to cross-validate this data set with the International Transport Association data set, because this is a more comprehensive data set, and which is also very expensive. And if we manage to get the same things from an open source data set and not have to pay, it would be very nice. And we would also like to use COVID-19 data to infer the potential of travel effects and travel restriction had on the spread of COVID-19. Thank you.
Good morning, everyone. My name is Sicheng Zhao. I'm from Queen's University. Today, I'm going to talk about the disease spread networks using percolation methods and age-based modeling. So the ICIR compartment model is widely used in mathematical epidemiology because it's mathematical simplicity. We have a nice SIR model, ODE system here, and there's a lot of extensions of SIR models here. But one of the flaws of the ICIR compartmental model is like it always assume like the mass action assumptions here, which means everybody in the population have the same contact ratio with everybody in, like any others in the population. So one key important difference is if you're considering like the mass action assumption, which is the blue line here, and some networks with social structures, they can have many difference in the epidemic dynamics. So commonly used methods to considering a social structure with compartmental models is using the network ideas and combine the SIR models with percolation process. So the networks in epidemiology always start with nodes and edges. The nodes in the networks always represent the individuals in the population, and edges means the disease-causing relationship between different individuals. So the typical process is introduced by Newman. So it's starting with the CM networks, which means the networks will not going to change with the time. So as a result, the epidemic result is not going to change with time as well. And the social structure here in the networks is given by the degree distribution, or how many edges contact to each of the individuals. And the network is constructed after you've given the social structure and assign the steps based on the degree distribution and randomly pairing the steps to form edges. And the SR models and the network itself is combined with the idea of the transmissibility T here. And we can get the probability of vertices being unaffected or being infected during the outbreak after the calculation. But one of the flaws for the typical version is there's no dynamic information, and it's only rely on the CM networks here. So one of the extension of the typical percolation process is the modification to talk about like partial immunity. There are two types of the partial immunity here, the leaky type and the polarized type. They have different like characteristics after you imply them into the networks. So the modification is based on a two-type model here, or sorry, two outbreak models here. The first outbreak is just a typical percolation process with naive population at the very beginning, and we introduce the idea of partial immunity after the first break, and we use the modifications to find the results of the second outbreak. So it's not the modification showing up here. It's not only just for the partial immunity discussion here. It also works for like more like outbreaks happens in the same population, and there's more like more than one, like multiple types of like edges and nodes in the networks. And another like modification is called the modified process. It's for like talking how to say to work with like the changing networks, like the edges and the degree even changing with the time. And one of the examples is the MFSH model here, where degree is not going to change, but the edges will reform like at any time. And a good point for this method is like it has a flow similar like the SR model, but based on the steps belongs to each type of the nodes. And we have a similar ODE system to reflect the dynamics of the epidemics. And we can get the basic reproduction number and other like epidemiological results from it. And another good points, we have ODEs and the disease developing dynamics with clear epidemiological interpretation. And it's also work with CM model and more flexible networks. So that's the idea of the percolation process. So I'm currently working now to create our packages for this three type of like percolation process. And also I want to use this idea of networks to deal with waning immunity here. And the most interesting topic I'm having now is to discuss like the disease control strategies based on the social structure instead of like the mass action assumption. So if you have any ideas or suggestions, I'm really happy to have them like during the poster session. Thank you very much.
Hi, good morning, everyone. I'm Open Mistry, a master's student at UNB, and I'm here to quickly talk about the work of our research group. Two of us are present here. We have Gaia and Jared, and then we have Bilal and Robert, who are not here with us right now, supervised by Dr. Sanjeev Sera and Dr. Superiore, and partnered by Dane Shepard from the Black Arcs. It's an interesting time to begin this talk because it's kind of a synthesis of the work the previous speakers have already spoken about. And based on Dr. Ferguson's taxonomy, it is a counterfactual near-term microsimulation. And it all is based on the kind of interventions that we had to deal with as modelers in terms of individuals and community level NPIs and PIs. For example, there's a subset of Government of New Brunswick's interventions strategies for Campbellton region in October 2020. And as other speakers have already said, modeling this as part of ODEs is obviously a possibility, but getting that parameter set makes sense with this is really challenging. And one of the ways to figure that out is have an individual level model of the entities or the vectors. And this is where our partner organization comes in. But this would be a snapshot of the CitySketch application by the Black Arcs. They recently got huge funding from Department of Defense and been covered by CBC. What they essentially do is take open GIS data for road network zoning and buildings. They take StatCan open data for census level, generate micro simulations, and using the Toronto area shared model for housing agents, we have them move around and generate an emergent contact network. And we take that and we put it into our contagion simulator. which looks eerily similar to the works presented before, because we do have extra components, compartments for hospitalizations and ICUs and deaths, obviously. We also have augmented the base SIR into diagnostic test-based discoveries, and the edges or the probabilities changing with doses of vaccination. So when we put this all together, we get results like this. We have individual infection trajectory as clouds, and obviously it's simpler to get a sense of it at a aggregated level as quantiles, 20%, 80%, and the median, similar to the, let's say, hurricane graph and destruction and so on and so forth. On the left, we are comparing school closures on infections, and on the right, we're projecting possible changes in infection trajectories due to change in testing strategies. Beyond this, the rest of the research group is working on optimization and scaling for bigger and more interconnected communities, parameterized comparison of OD and network models, and incorporating real-world mobility data and powering this up. And which brings us to the end of the talk. And thank you for your attention, and would love to hear from you in the poster session.
Okay, my talk is going to be very simple, and my name is Sana, and there are all J's in my life at the moment. Like all my supervisors start by J. So let's see, it's gonna be an between host modeling, not an. So what was the motivation for this research? Oh, sorry. So the motivation for this research was like in the last couple of years, there has been lots of outbreaks of mumps and sometimes other type of disease that you usually get vaccinated for them in childhood. And there is a myth that you're not supposed to get them again, but the outbreaks are happening. So we wonder why. And then there is also lots of research done that is actually like in epidemiology that finds a correlation between time since last vaccination and becoming infected. So we are guessing that vaccine-induced immunity is waning. So for that, so this is like we look for data to find it. And then when you want to actually model immunity, so adaptive immunity has two main parts. So it has like humoral immunity, which you talk about antibodies, B cells and all, or it has cellular immunity. But there's not much data available for cellular immunity. And I think it's more expensive. And also most of the time it's surrogate, like it's like measurements of interferons and all, which is not count of killer or helper T cells. So we decided to just stick with humoral immunity. And then so this is the type of data that we are supposed to use later on for fitting and model validation. So as you see, these are like post-second vaccine dose. And then it shows like the neutralizing antibody titer, how it is decreasing over the time. And this data set is longitudinal, so that's good because it is, they have measured it for about 10 years. So, okay. So here, like, let's say, even though it is in like between hosts, I find a lot of similarities at this point. So we just have like, oh, awkward. Sorry for thing. I think like, okay. It's because they have converted my talk from PDF to JPEG. So that's what you see here. There are weird parts. Let's ignore them. So we have uninfected, infected, and virus. At this point, it should be all good. It's similar to like between host models. And then, but the highlighted part is where like an antibody is interfering. And then what does neutralization mean? It means it binds to like a virus, a spike protein, and then neutralizes it, so it's kind of get cleared and doesn't cause a problem. So, but what produces antibodies? So usually antibodies are released by, are secreted by, I'm just gonna see, is this pointed? Yeah. Are secreted by short-lived plasma cells or long-lived plasma cells. And then, but they are last stage of like, it's a hierarchy of differentiation of cells. And usually it starts by a naive B cells. Okay, if I manage to do that, it's gonna be fun. So it starts by naive B cells, and then it keeps differentiated till you end up to have these two. But from where it's coming, at the beginning, like a naive B cells, a receptor recognizes the virus, and then it becomes activated. It doesn't do the job by itself. Like, of course, there are oversimplification. So it's gonna be with the help of helper T cells, we are not modeling that. So it becomes activated cell, and then activated B cell can do multiple type of differentiation. It can be a proliferation, or it can be differentiation to short-lived plasma cells, or differentiation to long-lived or memory cells. And this is to said, like, why this dude doesn't do anything at this moment? It's because at the beginning, like, memory B cells are produced, but they are quiescent, so they don't do anything at this stage. This is the modeling of a primary response. And then why this one look ugly? Because this thing all doesn't happen simultaneously. So at the beginning, so these two pathways are dominant when the virus is less and is getting higher, but when the infection is getting about to be cleared, so these two are more dominant. And that's what that function is trying to show. So this is our model. So we saw this part, and technically we just have added more like compartment to model to the stage that antibodies are actually produced. So let's get rid of this ugly part. So this is like a simulation of and we are at this stage of like estimating our parameters at the moment. And then so this is like what's happening in microliter of plasma. So this is labeled. I'm not going to talk too much over it, but the main point was that to get like the number of infected cell and the number of virus as the literature says. And then we are estimating our other parameters. How am I doing on time? Should I continue? Okay. So, and then now in the secondary exposure, any time after the first time you get infected or vaccinated, then we have other pathways to be, other pathways like from memory B cells to be activated. So they are quick. So that's why like the second time you get infected, you do better than the first time. So they directly can be long-lived plasma cells, which are releasing antibodies, or they back to being an activated cell and the whole story happens. So just look at the red part. So this is like what happens with the secondary exposure. So it's going to be added to that. And there is no simulation of that. And then this is the whole point of the project. So we want to see, actually the whole point is to model the course of vaccination. So like, do people need to get an extra vaccine, or we just need to shift the time of the second dose a little bit? So how do maternal antibodies affect the vaccine effectiveness and so on? Let's talk about it at my poster session. Thank you.